Hello, this is Dr. Liu, and in the previous video, we explained heat engines, primarily engines that we use to burn fuel and to get mechanical work out of that, and unfortunately, at the expense of having to exhaust some of that heat, and the efficiency can never be 100%. There was um, an ideal engine, the Cardinal engine that can do the ideal, basically the highest efficiency with a certain temperature at high temperature source and low temperature source. And today, the heat engines are referring to well, refrigerators and air conditioners or heat pumps. So let's talk about refrigerators, fridges and AC. And the goal is different over here because we're not trying to harvest work out of refrigerators. We're trying to remove heat from a low temperature source, that is the inside of the refrigerator, and try to exhaust that to a high temperature source, that is pretty much just the room. Okay, so the diagram is exactly the same, except the directions are slightly different. They're reversed. So let's draw three boxes. The one in the middle is the heat engine, and the top one is high temperature source. This bottom one is low temperature source. So this is okay. Here, let's write engine here. Okay, so again, there's more heat transferred in or out of the high temperature source, as we can imagine, low temperature source, and also work. But we're not trying to get work done. We're going to do work. We're going to do, for example, using a electric or it could be pneumatic compressor to compress certain liquid. So we're going to put work in instead of harvest work out. So we put work in, that causes the refrigerator or AC to suck energy, suck some heat out of the low temperature source and dump heat into the high temperature source. So if this is a fridge, the high temperature source is in the room, low temperature source is inside the fridge. If this were an AC, the low temperature source is inside of your AC room, and the high temperature source is outside the warm ambient. Okay, so the flow is still the same, except the direction has been reversed, right? In the previous version, the heat engine is you burn fuel, so at a high temperature here, you absorb heat and you have to exhaust some heat, and then the rest goes into work done. And now you're reversing the process. You do some work so that you can take heat out of a low temperature source, transfer, dump it into the high temperature source, but you dump more than you actually absorb, because the work also turns into heat and gets dumped in here. So now the goal is how much heat you can absorb from the low temperature source and under how much work you have to do. So you define a coefficient of performance of COP, and this is looking at how much heat you can absorb, you can take out of the cool environment, and then at the cost of how much work you have to do. And this work done is typically done by turning electrical potential energy into mechanical, right? So that's a work done there. So this can also be written because of the cyclic process. Okay, let's finish drawing this line here. The cyclic process, the after heat is absorbed, work is done, and then heat is dumped, the system, the engine returns to itself and absorbs more heat, gets more work done on it, and dumps more heat. Right, so that's repeating itself. So that coupled with the first law of thermodynamics, you must have no increase of your internal energy. So the work done and the heat absorption, they must be equal to each other. So here, the work done here as you can see, the work done should be this larger amount of heat minus a smaller amount of heat. We're always using positive quantity in such a discussion. These are all assumed to be positive. So this is the COP, the coefficient of performance of a refrigerator or an AC unit. And the ideal COP is calculated from the Cardinal engine or the reverse version of the Cardinal engine. And that is, you just kind of mock up the Q with a T. So T low, T high, minus T low. So that is the ideal. That means you cannot go any higher than that. Even reaching this ideal would be really difficult design challenge. Okay, so this is for refrigeration and air conditioning, which means cooling your room temperature below the ambient. But there's also heat pump. So let's see, refrigerator and AC. Let's move this over here because that's a bit more appropriate. I'll move this down one line. Okay, so for heat pump, what a heat pump usually is doing is it actually sucks heat out of the slightly cooler outdoor and then the exhaust heat into the indoor, combined with work done on it, so it warms the room. So this is what we normally don't really have in the cold northern U.S. We have to burn fuel directly just to heat our rooms. So in the southern part of the U.S., this could be a bit more efficient because you can turn it around into a refrigeration or the air conditioning to cool your room in the summer, and in the winter you reverse the process. You can suck heat out of the outside, which is cooler, and put it into the inside because you don't really get very cold winter temperature in the south. And if you have 60 degrees or maybe 55 degrees outside and you just want to keep 75 degrees or 70, so this could be doable with a heat pump. So the heat pump's goal is to generate heat to exhaust heat into the warmer room and at the cost of work done. So the coefficient of performance is defined as how much heat can you dump into the high temperature warm room divided by how much work you have to do to get that much heat. So it's different than the refrigeration, which means how much heat you can remove from the low temperature source that is inside of your fridge. So the two are different. And of course, there's also an ideal COP calculated from Carnot engine, and this would be the temperature instead of the heat. So T high minus T low. So that will be the ideal amount, and this amount is the actual amount. So let's do some examples on the right side. So first, let's assume in example 1 we have a COP equal to 2.5 fridge. That has 1000 watts. And how much time is needed to remove 10,000 joules of heat from inside the fridge. Okay, so we're looking for time, and we have a watt. So at least we know what the COP is, right? The COP is equal to 2.5. So that is the how much heat can be removed and how much work has to be done. So COP equals 2.5. That's how much heat has to be removed, how much work needs to be done. And how much heat do we want to remove? We want to remove 10,000 joules of heat. So let's put units in. And the work done should be power times time. Okay. So power is 1,000 watts. And 1,000 watts is 1,000 joules per second times the time. And 10,000 joules need to be removed. And we have this equal to 2.5. Okay, so now we have 1,000 T times 2.5 equals 10,000 joules. This is joule per second in left, and then 2.5. Okay, so let's keep the joules here, and T is equal to 10,000 over 1,000 is 10. 10 to 10 over 2.5 is 4 seconds. So in order to remove this much heat, 10,000 joules, we need 4 seconds. Each second removes 2.5, 2,500 joules of heat, because of the efficiency is, if you can do 1,000 joules of 1 joule of work, you remove 2.5 joules of heat. So that's a relationship. Okay, and in example 2, let's do the ideal situation. So let's say that we have two temperature sources. T high is equal to 300 Kelvin. This is a comfortable room temperature. And T low is 270. So it's a bit too cool or too cold for the southern temperature, southern U.S. temperature, and they're not used to our temperature in the north. So this could be the outdoor temperature. This could be their indoor comfortable temperature. So we're talking about a two separate situations. If this were a heat pump, we're trying to heat a room. Find the ideal COP. And then if this were not a heat pump and AC, basically the same heat pump, you run it in reverse and then find the COP in this case. So, okay, heat pump. We have the heat pump COP ideal is equal to high temperature over high minus low. So 300 over 300 minus 270. So 300 over 30. So this is equal to 10. And for AC, you turn the heat pump around, and we're going to use this ideal with low temperature on the top and high minus low. So 270 on top, 300 minus 270 on the bottom, and you have 270 over 30. You have a 9. So if you have a heat pump that works both ways, I would say it's kind of more efficient if you do it as I wouldn't say more efficient. It's the COP value is bigger if you run it as a heat pump to suck heat from outside and the exhaust into the room, and then if you run it as an AC, it's slightly less. Thank you.